Hi again. So in this video we will do some examples of drawing distributions and doing probability calculations with sampling distributions of means. Okay, so first we need some formulas. Remember, we saw the pattern in the simulation, but we can actually, statisticians have used those simulations to figure out formulas for what exactly the new standard deviation is. We know it's smaller, but we need to know exactly what the number is. So in this box kind of defines, again, the sampling distribution model of means. And it says if we're drawing from a population with a mean of mu and a standard deviation of sigma, then we have the following mean and standard deviation for the distribution of random samples. So we saw that our mean stayed the same, right? So this is saying mu sub x bar, the mean of the means, is the same as the original population mean. And then the standard deviation of our average of random samples, we can use sigma or we can use letter SD for that. That is sigma, the original standard deviation, divided by the square root of n. So this fits with the pattern we saw, that as n gets bigger, our new standard deviation gets smaller. So if you divide by a bigger and bigger n, even taking the square root, it's still going to be bigger, and you divide by a bigger number, you get a smaller number. So we could also kind of summarize this as saying our distribution x bar is distributed as normal with a mean of the original mean and a standard deviation of sigma divided by the square root of n. So that is our new distribution that we'll be working with, and we can find these numbers, put them into our online stat book or GeoGebra, our probability calculator, and we can calculate probabilities now. Woohoo! So we're going to do two different pages of notes here. The first page is starting with a population that is normally distributed. So this is important because it has to do with the sample size condition, right? If you start with the normal, you don't have a sample size condition. Any sample size is fine. But if you start with something that's not normal, population that's not normal to start with, then you have that sample size condition. So that's why we have two different pages of notes here. So that's something to watch out for when you're doing these problems. Look for that up front. Does it say anything about how the population is distributed? Okay, so here's an example. A person's measured glucose level 1 hour after ingesting a sugary drink varies according to the normal distribution with a mean of 125 milligrams per deciliter and a standard deviation of 10 milligrams per deciliter. Okay, so this is a measurement, so measurements tend to have a normal distribution to start with. The other thing to look out for is if it says a single measurement or if it says an average of memberships. If it's a single, it's just like what we were doing in the previous module. It's one value, we put it in our probability calculator. Okay, so if a single glucose measurement is made, define and draw the distribution. What's the probability that a single measurement is greater than 140 milligrams per deciliter? Okay, so define is writing out, now this is x because I'm not averaging, this is a single measurement, so x is distributed as normal with a mean of 125 and a sigma of 10 milligrams per deciliter. So that's defining. Then I'm going to go ahead and draw it. So I'm going to leave myself enough space. I know there's not a ton of room in these notes here, but I'm going to leave myself enough space to label it underneath and just draw it out the best I can. So I'm going to put the mean in the middle, 125, and go 1, 2, 3, 1, 2, 3, and this goes by tens, which is nice. 135, 145, 155, 115, 105, 95. Okay, so this is, I'm going to label over here since I don't have enough space. This is a single glucose measurement in milligrams per milliliter. Okay, and then define and draw. Now we can find our probability that x is greater than 140 equals, and I'm going to put this into online stat book. I'm just going to pause it because I didn't get that ready. Okay, here's our online stat book, our probability calculator. So I'm going to put in the mean of 125 and the standard deviation of 10. So far this is the same thing you're used to doing. And we want above 140. 0.0668. So let's go back to the notes. 0.0668. Okay, so that's finding a single measurement. Now, if we want to, and we need to, go ahead and use a sampling distribution. So it says if measurements are made on 3 different occasions and the mean result is computed. So this is how you know when you're going to be using the sampling distribution as opposed to the original one. Discuss each of the conditions required to use a sampling distribution for the average of 3 results. So first we're going to check the conditions, and then you'll see as we go forward, then we'll define our sampling distribution model, and then we'll find a probability. Okay, so let's talk about the conditions. Now the conditions are something that takes practice, and so don't feel confused or don't feel worried if it doesn't make sense on the first one. We're going to go through several examples and different types of examples. So but the most important thing is to kind of understand how to use these, how to apply these conditions in different contexts. So we're going to be looking at a lot of different contexts. Okay, so discuss the conditions to use the sampling distribution. Okay, I'm going to switch to green. So the first one was independence. So we need to know if we're taking measurements on 3 different occasions. This is, think of the same person, but they're being checked over time. Would these blood glucose measurements, blood glucose levels, be independent from each other? Or in other words, what would we need for those measurements to be independent? So I don't think you could take one right after another, because then not much would have changed, right? So I think what's important in this case is that we would take them on 3 different occasions. So maybe different times, different days. That's what would be important. Okay, so I'm going to write the 3 measurements would be independent of each other if spaced out on different days. Some of you who are going to be nurses probably know more about this than I do. Okay, and then with independence, remember, goes the 10% condition. But that is when we're sampling without replacement. Now this is kind of like the same person, so it's kind of like the original sample every time. So we're not really sampling without replacement here. It's not that we're putting the blood back in. It's just that this is not a surveying situation where you know, where you take 1 out and then 2 more out, and it's a with or without replacement situation. So I'm just going to say we're not sampling without replacement. So not an issue. Okay, so then 2 is randomization. Okay, again, this is a little bit of a unique situation because we have the same person, but we're doing 3 different measurements. So how could we randomize it? Could we maybe do different times of day? Of course, how it's spaced out with meals seems like that might be important. Someone who has a more medical background could probably make a better decision on that, on what would be needed. But I think if they, since they're from a single person, measurements are from a single person, but timing could be randomized. Okay, and then the last one is sample size. And because we are starting with a normal population, because measurements are usually normally distributed, any sample size is fine. So 3 is very small, right? But that's okay, because we saw in our simulation, even with a sample size of 2, that the distribution of the means was normal when the population was normal. Okay, so I'm going to write any sample size is fine. Due to normal population. Oops. Due to normal population. Okay, so again, these take a lot of practice, so don't worry, and we'll do more examples. Okay, now we get to the math part, which is a lot more fun. So define our sampling distribution. So define, now our distribution is called X bar because we're talking about the distribution of averages. And because our conditions are met, or we've talked about how to meet them, we are going to use a normal distribution. Now our mean stays the same, luckily, that's really nice, 125. But our standard deviation we know is going to be smaller because we saw even with a sample size of 2, we had a smaller standard deviation. So our new standard deviation, we're going to use this formula, sigma divided by the square root of n. And n is the number of things we are averaging. So in this case, 3. So our standard deviation is 10 divided by the square root of 3. Okay, so I'm going to get to my calculator for that. 10 divided by the square root of 3. If you have a calculator like mine that just transforms it, keeps it an exact answer, you probably have some kind of decimal button. This one has this arrow. If you have a TI, it's on the enter. It's a green diamond enter for the squiggly equal signs. So you can get a decimal like that. So I'm going to keep the 4 decimal places because we want to keep this really accurate. It's really sensitive to differences in standard deviation. So 5.7735. Okay. So when we do our calculations, when we do our, find our probabilities in using technology, we're going to use all these decimal places, okay? So I'm going to write for technology. I'm going to draw it though, and it'd be ridiculous to try to draw it with that many decimal places. So for that, for the drawing, I'm just going to round to 5.8. 5.8 for the drawing, okay? Now again, I didn't leave myself really enough room, so I'm going to draw it. I would try to make it to scale to that, but I don't think I have enough space. But we know it's going to be smaller, right? So our mean will be the same, 125, 1, 2, 3, 1, 2, 3. But this time our new standard deviation is 5.8. And you can also use online Statbook for these. You don't have to hand draw them, it's up to you. You can hand draw or copy and paste from online Statbook, but not GeoGebra because it doesn't do the scale right. It looks funny. Okay, so 125, I'm going to do plus 5.8, enter, plus 5.8, enter, plus 5.8, enter, and now I've got all my numbers, which makes it a little harder because I have less space and more decimals to work with, but I'll do the best I can. 130.8, 136.6, and 142.4. And then same thing going the other way. 125 minus, what was it, 5.8? 5.8 minus 5.8, enter, minus 5.8, enter. Okay, so then I've got 119.2, 113.4, 107.6. Whew, got it all in there. Okay, now the label is important on this because now this is not a single glucose measurement anymore, right? This is now an average of 3 glucose measurements. So I want to be sure to put that in my title. It could be above or below, because see how it changed the graph? This graph depends on what that n is. So this is only a graph for random samples of 3. So this is an average of 3 glucose measurements in milligrams per deciliter. Oops, I think above I wrote milliliter. I meant to say deciliter. Okay, so that is defining and drawing and labeling our model. Now, relative to the model in A means, like, if I could have, I would have kept it with the same center and then just showed that it got narrower, okay? Often when you see in books and other places, when you see these normal distributions, they all look the same width. So it's hard to remember that, oh, this is actually really narrower. So I like to try to draw it to scale to make it more concrete and help us all remember that this is a narrower distribution. Okay, so now we can find our probability. What's the probability that the mean of 3, so this is what tells us to use a sampling distribution instead of the regular distribution. The mean of 3 measurements is greater than or equal to 140, which is the same probability we found before. So now we're going to do probability of x bar greater than 140. I guess this one says greater than or equal. Remember, the equal sign doesn't matter for a continuous distribution. It does matter on the binomial, but on the normal it can be equal or greater than or equal, and mathematically those are the same. Okay, so now let's switch over to online stat book, and all we have to do is change our standard deviation to 5.7735. Enter. And because we're actually finding the same probability, that all stayed the same. And notice how the picture changed. This should match our picture. They did use more decimal places. They have, it's a little easier with technology. So that's great. More power to them. And then we have our new probability is 0.0047. 0.0047. Whoops, that's the right window. Okay, so notice how it got smaller because 140, let me shade our original one. Original 140 is right here, right? So that's our probability. Now 140 is way out here. Can't really even shade it, it's so far, well actually this is 142, so it's more like that. Because this got narrower, the probability got smaller, okay? So don't worry when that happens. Okay, now one more question. What is the 95th percentile for the average of 3 results from this person? Okay, so we're still using this same graph. I'll just make a sketch of it since we've already drawn it, but I'll just make a sketch. Remember 95th percentile? Percentile always goes to the left. So that means this area would be 0.95, and we're looking for this value. What would that be? Okay, so now I need to go back to my online stat book and the other link for the inverse normal. This is the inverse normal, and we're going to do, I'm going to stick with the below because that's the typical interpretation of percentile, but remember you could also do 5% above. That would be the same thing. So I'm going to put in my area of 0.95, and I have to re-enter my mean and standard deviation. The mean is 125, and the standard deviation is 5.7735. Hit enter so it adjusts. Okay, see how this kind of matches my picture here? And the value for the blood glucose is 134.497. It's important to put units on these. Let me go back to the notes. It's important to put units on these because these are values. They're not probabilities anymore. It's the value of a blood glucose measurement. So that's milligrams per deciliter. Okay, and I have room, so I'm going to write a sentence for this one. The 95th percentile for the average of 3 measurements, blood glucose measurements, is 134.497 milligrams per deciliter. Okay, so we might want to know this. Let's say if someone is above the 95th percentile, then we would consider them high risk. We would want to know what that was for them based on their measurements. And in this case, that would be above this level. Okay, great. So that is kind of a full example for starting with a normal distribution. In the next, on the next page, the next video, we will do an example when we're starting from a population that's not normal. Okay, see you in that video.